Hello. In the last two lectures of this week, we looked at elliptic integral based solution of large displacement analysis of beams, in particular a cantilever beam. It is an analytical solution that uses elliptic integrals. Today what we will do is to consider those equations that we wrote in the last two lectures and implement it in MATLAB, so that we understand the concept of elastic similarity that we discussed in the second lecture of this week. So, looking at this elastic similarity and how we can do those calculations in MATLAB, let us first look at the important equations which are shown here. The first equation shows how the length of the beam is obtained by integrating in the theta variable. So, here we are looking at d theta. So, theta variable. We also looked at a transformation or change of variables from theta to phi using these equations. So, that we will transform that to this equation, where the phi varies from sine inverse of 1 over p over square root of 2 to pi by 2. So, this equation is basically an equation in terms of p. So, p is a variable. Once we know p, we can get everything else. That is what we had discussed. Now, if we look at the geometric significance of that phi, when we change the variable from theta to phi, we know that is the angle that is shown here. For point B, we go up to P and then connect, that gives me phi B. Similarly, for point D, we go there, and point C, phi equal to 90 degrees, because if I go up and come down and look at the angle, that is 90 degrees. And for this point which you had called A earlier, phi is equal to 0. Okay. So, if I want to know W by L or X by L, they are given by these equations. What is W? W is the displacement in the W axis, and X is the displacement in the X axis. If I take a point D, at that point if I calculate this angle phi D by going up and finding this point and then joining it to O, then that inclination here is your phi D. If I want to know W of this, meaning that displacement, that is W, and this will be from here to here will be X. If I want to get that, then I have to, instead of this angle phi B, that will remain as it is. Instead of this phi, we have to put phi D, and same thing over here, same thing over here. For every angle, you get these displacements. And we also talked about extending it all the way, where phi goes to 0, that is the as if there is a vertical strut that is there, we apply a force on it, that is going to be, if this is the vertical strut, if there is a force there, that is going to buckle into this shape that we have. That is what we had discussed. Now, this H is given by this one, which we had also derived in the last lecture. Non-dimensional portrayal, if I take two different angles in that curve, phi 1 and phi 2, the difference in the W direction, X direction are given by these two equations. Again, the angles here that we have taken, that is where they figure in the elliptic integral solution. So, now let us look at a numerical example to understand how to implement these. So, we have taken a beam of length 1 meter, an Young's modulus, that of steel 210 gigapascals, 10 power minus 9 pascals, and we are taking rectangular cross section. That is why second moment of area is given as BDQ by 12, where B is the width of the beam cross section, which is 5 centimeters here, that is 5 in 10 power minus 2 meters, and D, depth of the beam, is 1 millimeter or 1 in 10 power minus 3 meters. The force we are varying from 0 to 12 newtons, and what we will use here will be our own code, in-house developed code for nonlinear beam elements using co-rotational beam elements, and some other data files that needs, and also use our elliptic integral solution. In MATLAB, there are two functions, elliptic f and elliptic e. This is the elliptic integral of the first kind and this is the elliptic integral of the second kind. That is what we need in the formulae. They are available in MATLAB. Okay. Now, here is the result of running nonlinear beam code that you will all have as supplementary material with this lecture, where we have taken the beam which is fixed over here and the force is applied there for different values of forces, starting from 0 in steps of 0.25 up to 3, steps of 0.5 up to 6, steps of 1 Newton up to 12. Beyond about 14 or 15, this fails to converge because there will be some kind of instability in the equations of the beam and finite element analysis does not converge. However, as you will see, elliptic integral solution has no problem in converging. Okay. This is with the finite element code. Now, from the finite element code, we have gotten the theta at the free end. That is, if I have a beam when it is going to bend like this, when we apply a force there, this here is theta L. That is shown in this blue curve. This is finite element solution. Okay. The dots here are the elliptic integral solutions. We can get this theta L from the elliptic integral solution also. On the other axis, so theta varies from 0 to 90 degrees, theta L, and if the beam completely goes like this angle will be approaching almost 90 degrees. Okay. This angle tends to pi by 2, we see that 90 degrees it goes there. Okay. That is this side. On this axis we have shown another curve which is the P curve. Okay. That is the P, meaning what we had in the equations, what is called the modulus elliptic integral, that is P. In the elliptic integral of the first kind, we have 1 over square root of 1 minus p square sin square phi, that is the P, and that is also done. And you can see the range of P, it is about from 1 over square root of 2, which is 0.7071 all the way to 1. That is the range of P. That is what will be unknown in all these problems. And theta L and P are related. So, where we have sin theta L is 2 p square minus 1. And in order to find that P, you have to solve this equation for given eta, which involves F, L, E and I. Okay. So, those are the things we need to solve, but here we are comparing what we got from finite element analysis and from elliptic integral solution, and their agreement is pretty good. As you can see, the dots which correspond to elliptic integral solution are right on the curve which was drawn using finite element analysis result. This is another way of looking at it. WL and UL are XL. So, this is XL by L, this is WL by L. WL meaning W at x equal to L, that loaded tip of the beam, and likewise XL is the x coordinate of the loaded tip of the beam. Again, the curves are using finite element analysis and the dots are from elliptic integral solution. They are agreeing very well here. And this is the code for that. We need to have this phi 0 when we had this cantilever that goes like this, we extend it back over there, and we also have this circular arc that was there, and if I go like this I get this angle, that is phi 0 or phi b if I call this point B. Okay, referring to the previous figures that we had, we have phi 0 that is in terms of P, and then we have the elliptic integral of the first kind and second kind that are given. What to notice is this thing, elliptic integral function elliptic f first kind in MATLAB takes the angle first and then the modulus square. Some books have this p square denoted as m, meaning that in the elliptic integral solution the integrand is 1 minus p square sin square phi. Some people write it as, instead of p square, they write m, and that m is what should go there, then you get the correct evaluation elliptic integral. We do that, we can get a WL and UL or XL, and we get these curves. So, this is the code in MATLAB, how to do it, a little close up view, so you can see the commands. Again, do not forget that you need to put p square there whenever you call elliptic integral of the first kind or second kind. Here, if you notice, we are putting a for loop where we are varying theta L and trying to get eta and p. Of course, p and theta are directly related, eta needs some computation. So, doing the other way is more difficult, that is, we are given the right hand side, that is eta, which involves L and F and E and I, getting p and then theta L is an inverse thing. MATLAB, some versions have elliptic integral inverse thing, some of them do not have, but I will discuss how to do that in the later part of this lecture. Now, here are the finite element analysis and elliptic integral solutions, where we are showing for different general values of phi, which varies from if I want to go all the way back here, right, when it goes like this, here is where phi equal to 0, phi equal to pi by 2 there. This is phi equal to 0, here is where phi equal to pi by 2. If I vary that, then I will get W everywhere and X everywhere. So, I can put all these dots. Again, the blue dots refer to elliptic integral solution, and the red curves are from finite element analysis for various forces that we have. Now, if I go all the way back to phi equal to 0, I generate this curve, that is what we want. So, as we vary phi from 0 to pi by 2, we get this entire curve for some force values. The other one, it is a different one, that will be accordingly some other curve, which we call elastica curve, and this elastic similarity is in exploiting this elastica curve. In fact, if we were to continue that angle from phi equal to 0 here, if I go negative, I go back and trace this entire curve. If I go positive beyond this, I trace this other curve. So, we get this what we had called nodal elastica. We will look at MATLAB code now to see how we can see the code generating all these curves that we have seen include nodal elastica by changing the phi angle. Let us switch over to MATLAB now. Here is the code that illustrates elliptic integral solution for large displacement analysis of cantilever beam. It uses nonlinear finite element beam code written by my student P. Sivanagendra back in 2006. This particular script of MATLAB combines the code that he had written along with the elliptic integral solutions, so that we can compare what we get. So, it calls a few M scripts that are required for the finite element correlational beam analysis, and it has some data files that we are already familiar with when we discuss this small and large displacement analysis, and all this code you are familiar, and we have the usual processing, pre-processing, and then the code calls this NLFEM beam for the displacements for given forces and the boundary condition. There is post processing that actually plots the deformed one. When it is done, it is going to look like this. So, here we are changing forces, let me magnify it. We are changing force from 0 value to 0.25, 0.5 newtons and so forth for the example values that we have considered. It is a 1 meter long beam that you can see, this is 1 meter, origin is where it is fixed here, and you can see how it deflects. Okay. Now, let me also show the elliptic integral that is implemented here. Elliptic integral solution, again we have taken length L equal to 1 meter, Young's model that of steel, second amount of area 5 centimeter by 1 millimeter cross section, and a force as much as 14, but we are actually changing the force for various values. Above, when I showed this finite element analysis, I will show you where the force is. Force is actually changed in a loop. Okay. There is a for I equal to size of f, and small f is where 0 in steps of 0.25 up to 3 newtons, and then 3.5 in steps of half a newton up to 6, and then 7 to 12 in steps of 1 newton, right. We have all that. Now, elliptic integral 1, in this particular case, I am taking a particular case of 14 newtons and try to get the W and XL, or here I am using the symbol UL, how we get elliptic integral solution for the deformation of the beam. If I look at that, right. So, we can see that this particular thing here, what I am showing here are these dots are the elliptic integral solution. Let me make it bigger. The dots are elliptic integral solution, and the curves are from finite element analysis. So, this is the UL or axial displacement, and this red one is the transverse displacement. You can see how well they agree with each other. The nonlinear beam code using co-rotation beam element, our own in-house code, and elliptic integral solution that we have implemented over here in the same code. They both are agreeing with each other. And let us also look at this particular plot, where we are plotting this blue curve is that theta L, that is the slope at the free end or the loaded end of the cantilever beam, versus eta, it is very small, but x axis here is eta, which is FL square by EI. This plot is there in the presentation, you can see the numbers clearly there. Eta is in the x axis, y axis we are showing where this theta L, it goes from 0 to about 90 degrees here, slightly less than that. As I increase force more, eta increases, eventually it is going to become 90 degrees. The red one is shown on the right side axis using that MATLAB command, which gives you a way of plotting two things in the same graph. So, this showing the p value, the p that we have with the modulus of the elliptic integral equation. So, there if you notice, p starts from somewhere here, which is actually 1 over square root of 2, which is 0.7071 all the way to 1. So, p range is limited, that we said in the lecture that we are discussing. Here you can see that really how p varies with eta. Eta is nothing but force once E, I and L are chosen. So, that is what we have in this particular case. So, by looking at elliptic integral, again I would like to point out that we have to put this p square there. Here I am calling p star for a particular f that we are doing to compare with the nonlinear beam code. If I were to change this value, instead of phi 0, if I were to put, let us say 0 itself, right, and run this portion. So, let me do that, and let me also, because it is going to go a little bit out of this thing, let me put, let us say 2 star that. Let me run this portion now. Elliptic integral solution, I would like to plot from 0 to that. So, if you look at this solution where we are going from, okay, let me make it bigger. It is previously it was phi b to pi by 2. Now, we have phi equal to 0 to pi by 2, we extend it beyond. This is what we had said, this elastic similarity. If this blue dot curve, if I were to make it vertical here, apply a load, it will buckle to that shape, that what we see, that phi 0. Let us actually run this again from a much smaller value, that is a good negative. Let us say I say minus 6 into pi by 2, and then here also I would go as far as 6 pi by 2, okay, and I will remove this pi by 2, that is not necessary now, it will be part of that. So, now if I were to plot it, let us not make it so large as 2 here, let us just take this much. Now, if I were to run this, only evaluate only the selection, let us see what happens. Now, the phi is increasing much less than 0. So, it is still running, the code is running, because you have to evaluate elliptic integral. We have taken about 15 that phi 0 that we have 15th step, we are going from a very large value that is 3 pi to minus 3 pi to 3 pi, it is taking time to plot it. Now, you see it is showing us what is called the nodal elastica. So, let me change this axis to see if there is more 2 star minus 1 1 minus 1 1, that is x min y min. Okay. So, let us see if that figure shows more. Yeah, we are seeing this. So, our cantilever beam is only this much. When I go up to phi equal to 0, it went. When I went to minus 3 pi, it bent like this, and similarly I went to up here, we have this. We see this nodal elastica that we had mentioned when we were discussing this elastica problem. So, we can play with this and we can see all of that all the solution that we see here depends only on one value p, that once we have, we can get this, and the p changes from curve to curve here. That is, if I were to take this one, that nodal elastica, the p is different from for that as opposed to this one, and so forth. Now, let us consider inclined load case. What if there is an inclined load in a beam? The way we had discussed was, we can take this primary beam that we have, that is BC prime, and get the elastica, then choose a point which we call T and draw a tangent line, the green line, whose length will be equal to the arc length TBC. So, the length, straight line length TC triple prime, that green line here, length of that is equal to arc length TBC. That is the length property of this elastica curve. So, if I do that, now if you see on this one, the force is vertically down, meaning that to the beam it is an inclined direction. But we already know the solution of this elastica, which depends on the value of p. If I have a horizontal beam of length BC prime, it bends like this. If I extend it, that is phi b that I have taken, take it all the way to 0, I get the rest of the curve. Any point t I take that has a particular phi, I have to go up and then this join this line, I get this angle phi. From phi to pi by 2, if I go, I get the length TC triple prime. Okay. So, this is how we can do, but if you want to know the deflection of this beam in this coordinate system, that is w prime and x prime. Now, whatever we have this w, l, x, l that we saw in the previous slides, they are in this coordinate system x and w. Now, instead of this x and w, if I want to go to x prime and w prime, let me switch out another color. So, this x prime and w prime. So, if I do that, then we will have to see how in this coordinate system we get these things with the transformation. What we have here is nothing but coordinate transformation. As Frisch-Fays in his book shows, as if you can turn around this coordinate system. Okay, he has turned what was like this, he has turned. Here we are keeping that and using analytical equations to transform, so that x prime w prime will be deflection of this point over here. That is, now from here to here will be x prime, and from here to here will be w prime. That is what you want, that we can get, provided we know w and x in the original coordinate system of x and w. So, you can handle an inclined load case. Now, if I look at the solution with inclined load, if I take this beam here and take that tangent can be easily obtained. So, how to do that? Here we have the angle theta, from there we get this phi, from there we get these loads, right. So, if we go back to the thing, here we had this angle here which is theta t. If I know this theta t, I will know how this curve is, and from there I can obtain the corresponding phi value, because this theta to phi change a variable, we know the value, we can get that phi, and once we get that phi, L phi can be obtained by integrating from 0 to that phi that we got. That will, if I do the integration of that elliptic of the first kind, where the eta is also where f e I square root is there, then I will get this L phi, I can call it, that is length from here to arc length all the way, this whole length or length of the original beam, I get that. Now, if there is a force P here, then we need to resolve a component along this and perpendicular, those are these. So, if I apply these forces, that will be same, it will be deforming to this shape, that is it will be deforming to this shape, the same thing that this beam which is fixed here would do, that is elastic similarity. So, to see that, we will see this in the MATLAB code in a moment. Here if I have a beam of length now is different, that is what we had called L phi in the previous slide, and here is the force which was actually straight for that beam, but straightly vertical, but here it is an inclined load based on that alpha that we have. When we take that, we have to put these new forces, inclined forces, these are second degree of freedom, first degree of freedom. I put those forces, then it bends like this, just like that. Now, what is x prime, and this is actually x prime, this is w prime. What are those? If I take this point, this would be x prime, and from there to here will be w prime. With this transformation we have that. Now, we look at the MATLAB code. So, we can see how if I were to take this beam, I get the same values for x prime and w prime as we did with the elliptic integral solution, where we had rotated the thing and found out. Okay. Let us look at the MATLAB code now. So, in this particular MATLAB code, we are dealing with an inclined load. We are going to show that with elliptic integral you can handle inclined load as well, and again this code also combines the nonlinear beam finite element code. So, we can compare the results of this. So, if you remember in this particular case, if I take this, we have plotted this elastica from phi equal to 0 to phi equal to pi by 2. So, this is our beam of length L with some transverse force, it has deformed to this, and this is the part of the nodal elastica. If I were to choose a point over here and draw a tangent, if I were to fix this right there and apply a vertical force here, it would deform from here to here. Length of this is more than the length of this, because as we know, any 2 points I take, when I do that integral that involves phi, I get the arc length. So, I get the arc length from here to here, which in the undeformed case will be tangent at that point. If you look at this beam, there is a vertical load, and that vertical load for this inclined beam is an inclined load. So, we can rotate this whole thing as we just saw in the slides. We can solve an inclined load problem using a horizontal beam of a smaller length. We have to find that length, and that is what we discussed in the slide. This is an implementation that we see, okay, the inclined one. And one more thing is, what I need to point out here, which we had in the slides, is getting the displacements in the local coordinate system of that inclined beam. The inclined beam t is what we had used the letter, those xt and wt are computed once you know the value of p, which I am calling here p star, in the coordinate system of the original beam, meaning, let me point out that we have a coordinate system here, this x and w. We know the coordinate of this point there, as well as this point T where we have drawn the tangent. Now, for this inclined beam with an inclined load, in this coordinate system I put x in this direction, w in that direction, then what is it? And that is given by actually this transformation that we have discussed in the slide. That is what it is, and these are the values. This xp, let me make it little bigger here. Okay. So, anyway, xp is 0.0932, wp is 1.1092, which we can check with a regular nonlinear beam code which does not have elliptic integral. But one more thing we need to know are the forces. If you put those forces, then we can verify that this beam would actually deflect to that shape. Now, if we see in general, if we are given a beam of length L prime and the load is given at an angle alpha, how do we proceed? In order to do that, what we do is we have to imagine that we have to turn it around. So, the beam inclined load should be like this, so that we get the equivalent beam which is horizontal and that has a length L. We want to know what that L is. For that, we have to imagine that we rotate this beam, so that this force becomes vertical. What is inclined? You rotate it until this force becomes vertical, then we have this curve that we want to find, but we know this angle theta, and theta and alpha are related. How are they related? They are related as theta equal to pi by 2 minus alpha, because if I complete this triangle, if this is 90 degrees here, this is 90 degrees, that is theta, alpha is pi by 2 minus alpha. Theta is pi by 2 minus alpha. If I know theta, I can get phi using this change of variable equation. Once I get phi, we have to find p such that this integral from phi to pi by 2 is equal to L prime, that is the given length of the beam. Okay, we have to solve this equation. This is where we have to have this inverse elliptic integral function, which all versions of MATLAB does not have, but I will show you how we can solve this equation nevertheless. We find p because p is here, sin square phi, that also is p, and overall integration we do, and this has from phi to pi by 2, that is in pi p, everything, this whole thing is a function of p. Now, given L prime, we need to find p, that is the equation we need to solve. Once we do that, we can get the length L, that we wanted that length L where the force will be vertical. So, we know that force acting here is same as force acting here to get to that, and we get this elastic similarity or elastica solution. We can find L, which goes from this angle theta equal to 0 corresponding phi, which is shown here, going all the way to pi by 2 gives us L. Once we know L, we know how to proceed with the problem. That is how we do it. Now, let us consider the moment load also now. There is a transverse load we considered. We discussed both the straight vertical transverse load as well as inclined load. Now, let us consider the moment load. As we had discussed second lecture, we have this extension of the rigid lever. So, we have this extension of the rigid lever E, and that E is chosen in such a way that there is a moment and the force are both felt at the point C. Now, here is where the large displacement analysis concept comes through clearly, in that in large displacement analysis we do the equilibrium in the deformed configuration. So, when the beam has bent like this, at point C, if there were to be transverse force F as well as a moment. So, at this point we want to apply a transverse force as well as a moment, right. If I want to do that, that moment should be such that there is a force which is displaced a little bit to the right. So, that F times E will give us the moment. At this point, the deformed configuration, at this point this moment will be acting. That is the reasoning behind this E. And from the geometry here we can see that E by H, this is E and H is this one. E by H is cosine phi C, and cosine h is equal to 2p by square root of f over ei. So, we basically get cosine phi, or we can calculate phi c from here. What we are saying is that when a beam is like this, here we know that phi is equal to sine inverse 1 over p square root of 2, whereas and here it is pi by 2, here it is pi by 2, that is phi there, and at point A phi equal to 0. What is it for point C, where we go up like this and join, that is my phi C. How do we get phi C? Here this is how we compute based on the moment value that is given, force value, Young's modulus, second moment of area, and P that we found, that we have to find. We have to find P. What is the equation for that? We know the length of the beam from B to C. So, arc length from B to C is the given length L. That is the problem we wanted to solve. There is a beam of length L with force F and moment M, then we get this in terms of phi C. We will see how we can compute. That is, if I go back and see this now, we have to find P in such a way that when I go from phi B, that is what this is, to phi C, that is I go from here to here along this thing here. When I do this elliptic integral of the first kind, I should get back L. Again we are given L, we have to find P here. P is the unknown. For every elastica, there is this characteristic modulus P that decides how the elastica is going to look like, and P is related to end load, and that kind of decides everything here. So, we have to find the P. Normally at the end would have been phi equal to pi by 2, but now we have a different expression phi C based on the equivalent moment that we will have force P, force F here, and then the moment which is F times E. We have to find this P. We have to find P such that this equation is satisfied. If we do that, let us take an example. So, where we have the force F here and then moment M here, 3 newtons, 0.4 Newton meter, the same length, same Young's modulus, same cross section that we have taken, we find the value of P. How do you do it? It is actually quite simple, because range of P is only from 1 over square root of 2 to 1. In that range, solving this equation is non-linear. We will plot it and see how it looks, and we can calculate the value of P, where length is in our case 1. So, let us plot it. I have plotted using MATLAB. So, from here to here, so you can see it varies P from 707.7071 to 1, and length is here. I need to go here, that is where length equal to 1. I have to find the corresponding P value. It is so close to that, this part we will zoom in and try to see when it becomes 1. So, here is where it became 1, then I have to find the corresponding value of P, which is 0.9984. It is very sensitive, we have to go up to 4 decimal places to get it right, and you can see that it is only the 5th decimal place that is changing. Okay. So, we take that P value here, that is how graphically we are solving, but you can also solve it computationally in MATLAB. You can use a find command and see when L is closest to 1 meter, that is the length here, what is the corresponding P if you do it in a loop. That is what we will look at to solve this problem using MATLAB. This is a solution where that moment load 1 gives you this curve, that is at this point if I apply a force F and a moment, this force and moment, that is equivalent to applying a beam of length 1.8257, as we will see in MATLAB. If I were to apply force F here, it will be like this, and what is E here? E is this horizontal span. This is our E, because that force F times E is what will be the moment that will be felt here in the deformed configuration of the beam, where the beam is straight with this is equivalent to a longer beam. This length we can compute, as we will see in MATLAB. This will be 1.8257 meters, then P equal to this value, M is 0.4, F is 3, we get this solution. Let us look at this example in MATLAB to understand what is happening. Now, let us look at the case of a transverse load as well as moment load using elliptic integral solution. Once again we will compare with nonlinear beam code, and what we see here, this LM is 1.8257, that is, if we look at the solution we will find out what it is. So, here elastica is the blue dots, okay. It starts from phi equal to 0, but our interest is from where this phi b, where theta equal to 0. You can see that red one is a finite element 1, we are plotting from here to here. For the finite element 1, if I look at the forces data file, we have second degree of freedom, 3 Newton transverse force, and then this is the theta degree of freedom, that is the transverse displacement. Here we have 0.4 Newton meter. So, the 2 degrees of freedom have the loads here for a beam of length 1 meter that we had. So, now if I look at this, we see that the equivalent force here, there is, if I were to apply a force over there for something that is as long as 1.8257 meters, if I apply a force here, at this point I would feel that force of 3 newtons as well as force times this one in the deformed configuration, this E that we had taken, that is whatever that we have here, that E will be the moment felt, and we chose that E so that the moment will be 0.4 Newton meter that we have taken in this particular case. The P is for the elastica curve, we need to solve that equation that we had seen in the slide. Here we have plotted L versus this P, when L for us is 1 meter. So, 1 is over there. So, let me zoom in to see what P value that we need to take. So, if I were to zoom in around 1, this is graphical way of solving an equation where we know the right hand side, we have to get the modulus of the elliptic integral. If I do this a few times, then I would get that. So, here up to 4 decimal places 9984. So, let us go back and look in the code of this moment 1 to see what p value we need to take for the elliptic integral solution. As said, we can actually solve it using bisection method, but now we are doing this graphically. The p value is 9984, you put it, we get this. If I were to change it, let us say I take off 2 decimal places, and now let me replot it to see what the effect is. This one, evaluate that part of the selection. When it is done, we will see how it would deviate. In fact, it does deviate. Now you can see I will make it bigger. So, what was like this now moves slightly away from the finite element solution, which is the correct one. So, we need to take p to high accuracy. In this case, we have taken it up to 4 decimal places, where the finite element solution and elliptic solutions agree with each other. If there are 2 transverse loads, then we have to basically have a P here, that P1 that we have, and the moment due to P2 should be felt here. Rather, at this point B, there will be effect of forces P1 and P2 and the moment, whereas this one feels only P2, except that this is a cantilever with slope equal to 0 here, where the cantilever with a slope which is non-zero. So, what we have here in this case would be an equivalent force P, which is equal to the sum of 2 forces that are applied on this beam P1 plus P2. For this portion, for this elastica, let us call this, there is a modulus P1. For this elastica, there is a modulus P2, because the rest of the portion behaves differently, because this one is just a transverse force and a moment. This one is only transverse force from here to here, another elastica. For this one, we know the final angle phi is pi by 2, whereas for this one we have to find phi b. So, corresponding to each force, there is a P modulus that is not known. For except the last one, this phi end will not be known. So, we have the this is phi b, in this case we do not know, the phi end is not known. So, if we have let us say n loads on a cantilever beam, there will be as many p unknowns as there are the number of loads, and number of phi unknowns will be 1 less, because for the last one phi equal to pi by 2, there will be 2n minus 1 unknowns. We will have that many equations in terms of elliptic integrals and we can solve. So, what we need to note here is that a differential equation, if you were to solve using finite element analysis, there will be many degrees of freedom, as many as number of nodes times 3, because a 2D beam element will have x displacement, y displacement and then rotation. 3 times the number of nodes are the number of degrees of freedom in finite element analysis, whereas here we can reduce it to 2n minus 1 equations and variables, where n is the number of loads. Even if there are 5 loads, we will only have 2 times 5 minus 1, that is only 9 equations. So, 9 variables, 9 equations, they involve elliptic integrals, but note that the p factors, p modulus values are only going to vary from 1 over square root of 2 to 1, that is not difficult to find, and the angle phi also is not going to change too much. It will be usually between 0 to 90 degrees when a beam bends with multiple loads. Of course, there will be complications when one force is down, other force is up, the beam develops points of inflection, which we will discuss in other later lectures. If you want to know further, all of what I have said is in this wonderful book by Frisch-Fays called Flexible Bars, where you can find lot more information than what we have discussed in the last 2 lectures and today's lecture in this week. Thank you.